ओके तो हम zigzag theorem कर रहे थे. टुडे we have to do the converse of zigzag theorem. So zigzag theorem follows from this theorem actually. So to prove converse, we show that if D is in dominion, then D tensor 1 is equal to 1 tensor D. So conversely assume that conversely assume that D belongs to dominion of U in S. We show that D tensor 1 is equal to 1 tensor D. D tensor 1 is equal to 1 tensor D. So let suppose we denote this S tensor S over U by in, which is this is true in S tensor S over U. So let A be equals to S tensor S over U. Let's denote this tensor product by U, tensor product by A. Then A is SS by system, or this tensor product is SS by system. Then A is SS is an SS by system, SS by system, where action is defined by this S times, so it's left S system, okay, S times element of S tensor S. Let's denote the elements of S tensor S by say X tensor Y here. Let's take it as X tensor Y. X tensor Y is equal to Sx tensor Y, and X tensor Y S is equal to X tensor Ys for all X tensor Y, for all X tensor Y belongs to S tensor S over U, and S belongs to S. Okay, with respect to this left action and right action, this S tensor S, it becomes an SS by system. So you can verify it easily. So you have to show that say ST of X tensor Y is equal to S of T of X tensor Y. तो इसी तरह से आपको लिखना है, आपको प्रूव करना है 1 टाइम्स X टेंसर Y इज इक्वल टू X टेंसर Y. इसी तरह से आपको राइट एक्शन की ये प्रॉपर्टीज चेक करनी है, दोनों प्रॉपर्टीज, और फिर आपको मतलब आपको एक और प्रॉपर्टी चेक करनी है which contains both right as well as right as system. That means you have to prove this say S times say X tensor Y T, this thing, it's equal to S times X tensor Y then T. तो जो बाय सिस्टम की प्रॉपर्टीज है वो आपको प्रूव करनी है बाय सिस्टम. तो ये आप वेरीफाई करोगे खुद कि वेरीफाई योरसेल्फ. दिस S tensor S is an SS by system. ये आप खुद वेरीफाई करोगे. Okay, so now we form a group that's called pre-abelian group with the help of the set A. So that's denoted by ZA with plus operation. That's a 3 plus operation actually. ZA plus बी द फ्री अबेलियन ग्रुप, बी आपको सिर्फ मोनाइट चाहिए एक्चुअली, बट हियर इट्स अ फ्री अबेलियन ग्रुप, बी द फ्री abelian be the free abelian group, where this ZA be the free abelian group, where what's this ZA, where ZA is this set, it is a set of finite sums, where A is set ZI AI. So here I will write it's a finite sum, okay, where this Zi is an integer, and AI belongs to A, where A is S tensor S or G. तो ये Zi है, और हम यहाँ पर ऑपरेशन प्लस है, मतलब आप दो फाइनाइट सम्स लोगे, उनका जो सम होगा वो भी फाइनाइट सम ही होगा, और द एलिमेंट्स ऑफ A with the coefficients belongs are integers. So this where Z is this, and the operation, what's the operation? And the operation is the addition, and the operation is addition. Operation is addition. यहाँ पर आप दो फाइनाइट सम्स लोगे, उनका सम भी फाइनाइट होगा. So फॉर अगर आप इसको वेरीफाई करना चाहो, let's take two elements here. Let x is equal to summation Zi AI. This is the finite sum, say I runs from 1 to n, and y equal to the finite sum, say let's take this as say Zi prime and AI prime. See I runs from say 1 to m. Then what's x plus y? Then x plus y is these finite sums is, so the sum of these finite sums is again a finite sum with coefficients are integers, and the elements which you are taking the sum, they are the elements from A. A's are A, AI primes are also equal to A. So you can write this as it's equal to summation I runs from 1 to n plus m. So let's write here, what should I write here? Let's write here, say let's write here Ri and Bi, okay, where Ri is equal to Zi for 1 less or equal to I less or equal to n, and it's equal to Zi prime. It's equal to, I'm not write Zi prime, it's here here we have so it's n plus 1, okay, n plus 1 less or equal to I less or equal to n. So here I should write here cannot write here Zi the Zi prime, it's equal to obviously it's a prime, but here I should the subscript, it's the sum is n plus 1 onwards, okay, n plus 1 less or equal to I, so it's n plus 1 less or equal to I less or equal to n plus n, okay, n plus 1 less or equal to I less or equal to n plus m. So what should write here, so that Rn plus 1 will be equal to Z1. So Rn plus 1, okay, Rn plus 1, it's equal to when I write I equal to n plus 1, it should be equal to 1 here. So I think I should write here so for I equal to n plus 1, it should be equal to 1, okay, minus n plus 1. So is it this I minus n so that for I equal to n plus 1 it's equal to 1, for I equal to n plus m it's equal, yes, this is like this, it's like this, Ri is equal to Zi for 1 lesser equal to I lesser equal to n, and it's equal to Zi minus 1 prime for n plus 1 lesser equal to I lesser equal to n plus m. And these AIs, this BI it's equal to AI for 1 lesser equal to I lesser equal to n, and it's equal to the prime for n plus 1 lesser equal to I lesser equal to n plus m. So this A prime, but the subscript is here again I minus n, okay, I minus n. So तो मतलब ये है कि आपने दो एलिमेंट्स लिए इस ज़ाड़ ए से, उनका सम भी इसी ज़ाड़े में है, क्योंकि ज़ाड़े के एलिमेंट्स इस टाइप के हैं जिनकी कोएफिशिएंट्स इंटीजर्स हो. So this is in Zade. Zade is an abelian group. It's an abelian group with addition obviously 0, with identity 0. But we need actually a monoid. हमें Zade असल में monoid चाहिए. Abelian group is a monoid. So this Zade plus is be the free abelian group where Zade is the finite sum over the elements of A with integral coefficients, and the operation is addition. So for this, let x be this finite sum, y be this finite sum, then x plus y is the finite sum, like this. Now we define action on ZA. This is the abelian group. The abelian group ZA plus, or simply ZA, is an SS by system. Is SS by system, okay? Is an SS by system, जैसे हमने इससे पहले प्रूव किया ना, SS by system की प्रॉपर्टीज. A को आपने प्रूव किया, वो SS by system है. अब आपको प्रूव करना है ZA, okay? Where action is defined by, where action is defined by, what's the action here? It's S times the finite sum ZA AI is equal to. तो जब मैं लेफ्ट एक्शन डिफाइन करूँगा, इसका आउट, अब ये जो एलिमेंट है ना, ये फाइनाइट सम, ये ZA का एलिमेंट है. तो अब जब आपने उसको लेफ्ट साइड से S से मल्टीपल किया, तो आउटपुट भी ZA का एलिमेंट होना ही चाहिए. दिस इज इक्वल टू ZI देन SAI क्योंकि A का ही एलिमेंट है, बिकॉज A इज लेफ्ट एस सिस्टम, जो आपने इससे पहले वेरीफाई किया. एंड समेशन ZI AI, अब राइट एक्शन हम डिफाइन करेंगे. दिस इज इक्वल टू समेशन ZI AI S. अब A को आपने ऑलरेडी प्रूव किया, वो राइट सिस्टम है. AI A का एलिमेंट है. So this is also one can easily verify that. Also this thing holds. This you can easily verify that. This one, S times x plus y is equal to Sx plus Sy, and x plus y times s is equal to xs plus ys. So for all x and y in ZA, s in s, where these x, y, they belong to ZA and s belongs to s. इसको आप इजीली प्रूव कर सकते हो. दिस वन, अगर आप इसकी जस्टिफिकेशन चाहते हो, दिस व्हाट जस्टिफिकेशन. So let's take two elements, that x is equal to finite sum ZA AI and y equal to the finite sum, say it's ZI prime AI prime, be members of what? Members of Z A, and S is a member of S. Then what's this? S times X plus Y. By definition, it now you apply this. This it's called summation Zi AI plus summation Zi prime AI prime. अब चूंकि एक ही सम होगा फिर S इसके अंदर जाएगा. इट्स इक्वल टू समेशन, जो इसकी डेफिनेशन है, एक्शन की डेफिनेशन, इट्स इक्वल टू Zi S AI प्लस समेशन Zi प्राइम S AI. ओके, दिस बट दिस इज इक्वल टू. अब हम S को बाहर निकाल सकते हैं. पहले आपको ये सम को क्लब करना, एक ही सम लिखना है, फिर आपको S अंदर लाना है. ओके, और फिर आप इस सम को ब्रेक करना है, आपको अलग अलग फिर से लिखना है, और फिर आपको ये S बाहर निकालना है इस सम से. इट्स S टाइम्स समेशन Zi प्लस S टाइम्स समेशन Zi प्राइम AI प्राइम. So that's equal to Sx plus Sy. Sx plus Sy. So in a similar way, you can prove that this x plus y times s, x plus y times s is equal to xs plus ys. So that's very simple. Okay, that you can prove. So similarly x plus y times s is equal to xs plus ys. xs plus ys. तो एक्चुअली हमें प्रूव करना है डी डोमिनियन में है. तो डी डोमिनियन में होने के लिए और ना डी डोमिनियन में है, आपको प्रूव करना है डी टेंसर 1 इज इक्वल टू 1 टेंसर टी. तो आपको डोमिनियन की प्रॉपर्टी यूज करनी है. यू हैव, आपको दो मॉर्फिज्म्स डिफाइन करनी है, बीटा गामा फ्रॉम द सेमी ग्रुप एस टू सम सेमी ग्रुप, जो आपको कंस्ट्रक्ट करना है, या मोनाइड यू कैन से सच दैट दे एग्री ऑन यू, then they must agree on D because D is in dominion, और from that equation they agree on D, वहाँ से आपको मिल जाएगा D टेंसर 1 is equal to 1 टेंसर D. तो इसके लिए आपको वो मोनाइड एक्चुअली चाहिए, मोनाइड चाहिए, और वो दो मॉर्फिज्म्स आपको एक्चुअली चाहिए जो एग्री करें ऊपर. फिर आप डोमिनियन की प्रॉपर्टी, डोमिनियन की डेफिनेशन यूज करोगे, तो वहाँ से डी बीटा डी गामा के बराबर हो जाएगा. तो वही एक्चुअली वही मोनाइड हम अब नेक्स्ट डिफाइन करेंगे. सो वी नॉट डिफाइन बाइनरी ऑपरेशन ऑन, we now define a binary operation on S क्रॉस Z. आप प्रूव करोगे S क्रॉस Z मोनाइड है, तो S भी मोनाइड है, Z भी मोनाइड है, इनका क्रॉस प्रोडक्ट तो है ही मोनाइड अंडर कंपोनेंट वाइज ऑपरेशन. बट हियर वी आर नॉट यूजिंग द कंपोनेंट वाइज ऑपरेशन, में डिफरेंट ऑपरेशन यहाँ पर लेना है. by the following rule. Okay, by the following rule. So how do we define? Let's take the element of two elements. So let px and qy, suppose they belong to S cross Z. तो Z में आपको पता ही क्या है, दोस्त फाइनाइट सम्स. S तो केवल मोनाइट है, तो P और Q S में है और X और Y Z में है. So we define product like this: Px Qy is equal to PQ. Then it's here Py plus XQ. अब आप कहोगे कि ये ऑपरेशन हम कैसे याद रखें. यू कैन ट्रीट दिस एज x by p, ओके, एंड दिस एज y by q, इसको याद रखने के लिए. then let's do addition. So what's the addition? It's here py plus xq. Okay, py plus xq divided by pq. It's here py, or you can say xq plus py. That's also correct because z is commutative. It's x cube plus py. आप लिख सकते x cube plus py over p cube. तो जैसे आपने px को डिनोट किया x पे p से क्यू y को आपने लिखा y पे q, इसी तरह से आप इस क्वेश्चन को लिख सकते हो p क्यूब कॉमा x क्यूब प्लस py, वही आपने लिख दिया p क्यूब देन py plus x cube. So this is the operation here. And with respect to this operation, it's a monoid. This S cross ZA is a monoid. और इसकी जो आइडेंटिटी है वो है then S cross ZA is a monoid. And its with identity इसकी जो आइडेंटिटी है वो क्या है, S की आइडेंटिटी तो 1 है और ZA की आइडेंटिटी 0 है, तो इसकी आइडेंटिटी जो होगी वो 1 0 है. You can easily verify that 1 0 with identity 1 0, where 1 is the identity of S and 0 is the identity of ZA. तो ये इसकी आइडेंटिटी, ये मोनोइड है. Obviously this operation is closed because PQ is in S. PY जो है P क्योंकि S का एलिमेंट है, Y ZA का एलिमेंट है. अब चूंकि ZA जो है ना वो लेफ्ट हैंड सिस्टम है, तो PY भी ZA का एलिमेंट होगा. इसी तरह X ZA का एलिमेंट है, Q जो है आपका वो S का एलिमेंट है, तो XQ भी ZA का ही एलिमेंट है बिकॉज ZA इज राइट एस सिस्टम. और इनका सम भी ZA का ही एलिमेंट होगा बिकॉज ZA इज ग्रुप विथ रिस्पेक्ट टू द एडिशन. तो ये ZA का एलिमेंट, इसकी सेकंड एंट्री ZA की है, फर्स्ट एंट्री S की है, सो इट इज एन S क्रॉस ZA. तो इट्स क्लोज विथ रिस्पेक्ट टू दिस ऑपरेशन. सिर्फ आपको एसोसिएटिविटी चेक करनी है, चेक एसोसिएटिविटी. तो वेरीफाई एसोसिएटिविटी, इसकी एसोसिएटिविटी आप चेक कीजिए. ओके, तो वो आपके लिए असाइनमेंट है, इसके एसोसिएटिविटी चेक करना. इसने उसमें से कुछ किया है, आप उसको देखिए अच्छी तरह से. तो इसने वो किया है इसके एसोसिएटिविटी. ओके, वो आप देखिए, दैट्स वेरी सिंपल, इट्स नॉट टू डिफिकल्ट. आपको सिर्फ बाइनरी ऑपरेशन अप्लाई करनी है. इसकी डेफिनेशन यू कैन इजीली गेट द एसोसिएटिविटी ऑफ दैट बाइनरी ऑपरेशन. तो अब आपके पास मोनाइड आ गई. अब आप S से लेकर इस मोनाइड तक मॉर्फिज्म्स डिफाइन करोगे. सो लेट्स डिफाइन बीटा गामा फ्रॉम S to S cross ZA by S beta is equal to S0. पहला फर्स्ट एलिमेंट S का, सेकंड इज द आइडेंटिटी which is the identity of ZA, and S gamma is equal to what's S gamma? It's equal to S, then S tensor 1 minus 1 tensor S. So second, Z is group with respect to addition, so minus is defined there. So it is the additive inverse minus. तो ये दोनों बीटा तो है ही मॉर्फिज्म बिकॉज बीटा ऑफ S1 S2 is equal to S1 S2 0, that's equal to S1 0 S2 0. that you can easily verify that S1 0 S2 0 is equal to S1 S2 0. that's very simple. but second जो आपको चेक करना है, so first to verify that beta is morphism. Beta is a monoid morphism, is a monoid because you are in monoids, monoid morphism. So for this, let's choose two elements, that S1 S2 is S, then S1 S2 of beta, it's equal to S1 S2 0, and you verify that this is equal to S1 0 S2 0, that you verify. Okay, this thing, it's S1 0 S2 0, and that's equal to S1 beta S2 beta. And image of the identity, because the identity of S is 1, beta 1 is equal to 1 comma 0, which is the identity of S cross ZA, which is the identity of S cross ZA. So therefore beta is a monide morphism. Therefore beta is a monide morphism. Now we show that gamma is a monide morphism. Okay, gamma is a monide morphism. So again, let's choose 2 elements from S. Let S1, S2 belongs to S. Then we show that S1, S2 gamma is equal to S1 gamma, S2 gamma. So then S1, S2 gamma, by definition it's equal to S1, S2, then S1, S2 tensor 1 minus 1 tensor S1, S2. So this is equal to S1 times S2 tensor 1, and this is 1 tensor S1 S2 is equal to 1 tensor S1 times S2. So because it's the property of the action, okay? So that's the property of the action, left action and right action. It's equal to S1 S2 minus S1 times S2 tensor 1. It's not minus here, sorry, it's minus 1 tensor S1 times S2, by definition of right action and left action. And now you verify this. It's equal to S1, then it's here then it's equal to S2 tensor 1 minus, not S2 tensor 1, it should be equal to here S1 tensor 1 minus 1 tensor S1 times S2, then S2 tensor 1 minus 1 tensor S2. अब इनका प्रोडक्ट आपको इट्स इक्वल टू S1 S2, then S1, then S it's equal to S1 S2. Okay, first entry is S1 S2. What's second entry? That's equal to so what's the operation? What's the operation here? Let's see the operation again. It's equal to PQ, then PY and XQ. Okay, PY and XQ. Okay, PY is income product. Okay, PY is this, PY, then plus XQ, PY and XQ, X is this. So I will do it in the next page. Okay, so let's try to verify it. Verification. So let's find this product S1, then S1 tensor 1 minus 1 tensor S1, its product with S2, then S2 tensor 1 minus 1 tensor S2. Let's see this product. By definition it's equal to S1 S2. पहली एंट्री तो आ ही रही है. Second is the S1 times this product, S1 times, or you can write this time as S2. Okay, let's write this S1 times S2 tensor 1 minus 1 tensor S2. Okay, then plus it's here S1 tensor 1. Okay, S1 tensor 1 minus 1 tensor S1 it's S2. Okay, this is equal to S1 S2. Now what's this? It's S1 S2 tensor 1, S1 S2 tensor 1. Okay, minus this will be here S1 tensor S2, the product of the action, left action. Then plus here it's here you can say it's equal to S1 tensor S2, S1 tensor S2. Then minus this one, it's 1 tensor S1 S2. Now this S1 tensor minus S1 tensor S2 plus S, it's equal to 0. It is the identity. These two will go, and it is the identity of ZA. So it's equal to S1 S2 with S1 S2 tensor 1, S1 S2 tensor 1 minus 1 tensor S1 S2. So that's the verification. This product is equal to that S1 S2, which is S1 S2 tensor 1 minus 1 tensor S1 S2. So but this one this is equal to S1 beta. Okay, मैं फिर पहले पेज पर आ गया, previous पेज पर. This one is S2 beta. Okay, it's gamma here, it's not beta, it's gamma. It's equal to S1 gamma then S2 gamma. अब सिर्फ आपको देखना कि आइडेंटिटी कहाँ जा रही है. व्हाट्स द इमेज ऑफ आइडेंटिटी? दैट शुड बी आइडेंटिटी. अगर आपको प्रूव करना है कि ये मोनाइड मॉर्फिज्म है. सो नाउ लेट्स चेक द आइडेंटिटी. इमेज ऑफ 1 अंडर गामा, इट्स इक्वल टू 1. Then obviously it's 1 tensor 1 minus 1 tensor 1, but 1 tensor 1 is the zero element of the group. So which is identity? Which is the identity of? Which is the identity of? Which is the identity of what? Which is the identity of S cross ZA. So therefore gamma is a monide morphism. It's a monide morphism. Now we show that beta and gamma, they agree on U. So for this we see that since what's rho? Since rho because here S tensor S over U is equal to S cross S, a quotient of S cross S by rho. Since rho is the congruence, यहाँ पर कौन सी कॉन्ग्रुएंस है? यहाँ पर ए बी फिक्स, ए बी एस है, बी बी एस है, और आपका एस जो है वो यू है, जो आपने टेंसर प्रोडक्ट में डिफाइन किया था ना, ए टेंसर एस, ए टेंसर बी ओवर एस. ओके, रो इज द कॉन्ग्रुएंस generated by this element, generated by this relation, और ये इससे जनरेट हो रही है. एक्चुअली यहाँ पर क्या था? ए एस बी देन ए कामा एस बी. तो ए की जगह पर एस के एलिमेंट्स हो गए एस यू, और यू का वहाँ पर एस का एलिमेंट मूव हो रहा था, यहाँ यू का एलिमेंट मूव होगा एस यू टी देन एस यू टी, सच दैट these are the pairs. Okay, these are the order pairs such that this S T, they are both in S and U is in U. So अगर आप S की जगह पर भी 1 लोगे, T की जगह पर भी 1 लोगे, तो आपके पास यहाँ पर U1 आ जाएगा और यहाँ पर आ जाएगा 1U. तो दैट मीन्स U1 and 1U they belong to, so therefore U1 and 1U, this pair, it belongs to R, and which is subset of rho, because rho is the congruence generated by this R. So which implies that the U1 pair, it's tau related, it's rho related. Okay, I don't know whether you have written there rho or tau, whether is it rho or tau, you verify that. Okay, तो आपने इसको रो से डिनोट किया कि टाउ से डिनोट, जो आपने कॉन्ग्रुएंस जनरेट किया ना आर से, वो आप देखिए. This is a U1 of rho class of U1 is same as rho class of 1U. Okay, because they are rho related. But what's this rho class? They have denoted, you have denoted those we have denoted those rho classes of the elements by the tensor product. Okay, so this rho class of U1 means U tensor 1, and rho class of 1U means 1 tensor U. So this implies u tensor 1 is equal to 1 tensor u. So therefore for all u in u, okay, for all u, therefore we have the following: u beta, which is equal to u1, and that's equal to it's u0 here, not u1, definition of u, and this 0 is equal to u tensor 1 minus 1 tensor u, because u tensor 1 is same as 1 tensor u, so this difference is 0. But now this one, it's the definition of gamma, it's gamma u, it's u gamma, it is u gamma for all u in u. So for all u in u, beta u is same as gamma u. That means beta and u, gamma, they agree on u, but d is in dominion. This means that d beta is equal to d gamma, because d belongs to the dominion. Okay, so this means, what's the definition of d beta? It's equal to d1, okay, d0, d0. This is equal to d, what's the definition of gamma? It's d tensor 1 minus 1 tensor d. So these two ordered pairs are equal. It means that 0 is equal to d tensor 1 minus 1 tensor d. So this implies d tensor 1 minus 1 tensor d is equal to 0. So that means these two elements, they must be equal. So as required. So that is proof of this theorem. So from this we obviously get the system of equations, because d tensor 1 equals to 1 tensor d gives us the system of equations. So that's the next theorem. Let u be a submonad of a monad S, then d belongs to dominion of u in S if and only if d belongs to u, or there exists a system of equations of the following type. So this d is in dominion if and only if d is in u, or there exists a system of equations, okay, system of equations of the following two. That's why it's called actually zigzag theorem. वो जो system of equations होगी वो zigzag type की वो equations होगी. Following system of equations: d equal to u naught x1, u naught is equal to, it's you write here u naught y1 here. Let's use standard one. U naught y1, u naught is equal to x1 u1, then this u1 y1 is equal to u2 y2, and then here it's equal to x1 u2 is equal to x2 u3. अब इसके बाद ये u3 यहाँ जाएगा, it's u3, और ये y2 यहाँ जाएगा, u3 y2 is equal to u4. It's like zigzag type ना, तो ये एलिमेंट्स यहाँ वापस आ रही हैं. सो देन अब आपके पास u4 आ गया, और x2 तो यहाँ पर ये x2 नीचे आ जाएगा और ये u4 आगे जाएगा. x2 u4 is equal to x3 u5, और इन जनरल स्टेप जो आपके पास होगा वो होगा ये u2i minus 1 yi, okay, is equal to, so it's equal to u2i yi plus 1 then this is here x2, so this is y2, this is x2, so if it is here y, then it should be here xi u2i, so that u2i, it will go here. Okay, xi u2i is equal to xi plus 1 u2i plus 1. Okay, for I equal to say, so यहाँ पर I की वेरिएशन अब 3 onwards होगी, 3 4 से up to let's write here say m minus 1. अब m minus 1 जब होगा तो यहाँ पर 2u2m minus 1 होगा, तो यहाँ पर आ जाएगा u2m minus 1 ym, that is equal to u2m. ये फाइनल स्टेप होगा, यहाँ पर u2m यहाँ पर ये टर्मिनेट होगा, एंड xm u2m जो होगा वो वापस d के बराबर आ जाएगा. So d is in dominant if and only we have this set of equations. अब डोमिनेंट देखिए, डोमिनेंट में आपके पास क्या है डेफिनेशन, आपको सारी मॉर्फिज्म्स चेक करने, फिर आपको देखना कि दे एग्री ऑन यू, फिर आपको देखना कि वेदर दे एग्री ऑन टी और नॉट, तो तब जाके डी डोमिनेंट में आ जाएगा. बट फ्रॉम दिस थ्योरम यू जस्ट ट्राई टू सी दैट इफ डी हैज दिस सिस्टम ऑफ इक्वेशंस देन डी इज इन डोमिनेंट, देन डी इज इन, या अगर डी डोमिनेंट में है तो आपके पास ये सेट ऑफ इक्वेशंस होगी, तो इनसे आप कुछ रिजल्ट्स निकाल सकते हो इन इक्वेशंस से. So this let's write these system of equations and let's denote those equations by 1. Okay, so proof, suppose we have system of equations of the type 1. Suppose okay, let's because there are elements कहाँ हैं, ये elements जो है ना आपके पास जो है where xi yi they are in S, 1 less or equal to I less or equal to m. Okay, and these ui they belong to u for 0 less or equal to I less or equal to m minus 1. और ये जो u के एलिमेंट्स हैं ना, इनको हम कहते हैं supine elements of this zigzag, supine of this zigzag. Okay, तो वो मैं आगे इसकी डेफिनेशन लिखूंगा supine element की. So ui's they are in u, okay, and xi's and yi's they are in S. Proof. Assume that D satisfies the set of equations 1. आपको प्रूव करना है, we show that D is in dominant, we show that D belongs to dominion of universe. तो डोमिनेंट में प्रूव करने के लिए आपको क्या करना है, you have to choose any two morphisms. let beta gamma be morphisms from S to T, monoid morphisms obviously, be monoid morphisms such that they agree on u, such that u beta is equal to u gamma for all u in u. आपको प्रूव करना है d डोमिनियन में है, that means आपको प्रूव करना है d beta is equal to d gamma. Now let's find d beta. Now d beta, what's d in the previous, because d satisfies the set of equations given by 1, so what's d? D is equal to u naught y1, so let's substitute that value. D is equal to u naught y1 of beta. Now beta is a morphism, it's equal to u naught beta and y1 beta. Again from the set of equations 1 आप लिख सकते हो यहाँ पर ना, यहाँ by equation is 1. Okay, by equation is 1. Okay, now again u naught, what's u naught? U naught is x1 u1, u naught is x1 u1. From that set of equations u naught is x1 u1. Okay, it's here x1 u1 of beta. Okay, so आपको गामा तक पहुंचना है. So let's first apply this. U beta is equal to U gamma for all U in U. So U naught beta is equal to U. So let's write here U naught beta is equal to U naught gamma. Okay, then it's here Y1 beta. Now this U naught, it's equal to what? It's equal to x1 u1 of gamma, and this is here y1 beta. So what's U naught? U naught is equal to x1 u1. It's again by equation is 1. By equation is 1. Okay, by equation is 1. Now you apply the morphism property of gamma. It's equal to x1 gamma, then u1 gamma, then y1 beta. It's equal to x1 gamma. This one u1 gamma is same as u1 beta. Then it's here y1 beta, and this is equal to x1 gamma. Now since beta is morphism, it's equal to u1 y1 beta, but u1 y1 is equal to u2 y2. It's equal to x1 gamma. This one is u2 y2 of beta. Okay, so now it's here x1 gamma. This is here u2 beta, y2 beta, because beta is morphism. This is equal to x1 gamma. Now u2 beta is same as u2 gamma, because beta and gamma are equal on the elements of u, at every element of u. Now this gamma is morphism, so we can club these two. It's here x1 u2 gamma. It's equal to x1 u2 gamma and y2 beta, and this is equal to x2 u3 gamma y2 beta. And you continue this process, you will see this xm u2m minus 1 of gamma and ym beta. But xm u2m minus 1 is u2m. Okay, so is it xm u2m minus 1 is so if it's u2m of gamma, then there is some problem. I want d gamma, and finally I should obtain this d gamma. So here it's gamma on this side, u naught y1. Okay, so let's see the set of equations again. So d is equal to u naught y1, and u2m minus 1 ym is u2m. Okay, and this is here xm. Okay, let's see this. So u naught. Okay, so u naught. So let's try 2. Okay, so I should obtain okay, it's gamma. Here x1 gamma. So okay, it's x1 gamma u1 beta, u2 y2 beta. Okay, this is u2m. Okay, x1 gamma u2 gamma. So let's see it here. So it's xm u2m minus 1 ym. So it's x m u to m minus 1, that's equal to u to m, that leaves beta of u to m. So where is the problem? This मुझे finally gamma t चाहिए. Okay, I want gamma t. Actually, I want gamma t. But here if I write it's gamma 2m, gamma 2m is same as beta 2m, then it's beta 2m beta. तो ये ym किसी तरह से फिनिश होना चाहिए, जहाँ पर xm खत्म हो रहा है, xm पर ही टर्मिनेट हो रहा है. Why? So let us see it again here. So we have these system of equations for D. So u naught is equal to, so that means u to m. Okay, right. तो यहाँ पर देखिए ना आप, u to m किसके बराबर, इट्स इक्वल टू u to m minus 1 ym. तो मैंने एक्चुअली zigzag equations गलत लिखी है, वहाँ पर मैंने equations को गलत लिखा है. So let's see it again. It's u naught 1, that's right. So what's u naught? U naught is x1 u1. x1 u, right? Okay. It's fine. It's all right. Okay, x m u to m minus 1 is not u to m. U to m minus 1 ym is u to m. Okay, so it's all right. So this is not u to m. This is equal to, first we apply this one, x m gamma, then u to m minus 1 gamma, then y m beta. Now u to m minus 1 gamma is same as what? It is same as u to m minus 1 beta, because beta and gamma are equal on u, they are equal on u. This is your ym beta. Now you can apply the property of morphism here. It's xm gamma, this one is u to m minus 1 ym beta, and it's equal to xm gamma, u to m minus 1 ym is u to m beta. Okay, this is equal to xm gamma. तो आप एक्चुअली आपने कहाँ से स्टार्ट किया? d बीटा से. ओके, so xm gamma, this u to m beta is same as u to m gamma. तो यहाँ पर आपने लिखा बाई इक्वेशंस, पहले बाई इक्वेशंस 1, जो आपने इक्वेशंस 1 लिखी ना, वहाँ से आपने लिख दिया u to m minus 1 ym is equal to u to m. अब यहाँ बीटा और गामा इक्वल है ऑन यू, सो दिस इज इक्वल टू, नाउ दिस इज इक्वल टू एक्स एम u to m gamma, but this one xm u to m, it is equal to d gamma. So therefore d beta is equal to d gamma, so which implies d is in the domain. Okay, so whenever we have that those set of equations, then d is in the domain. So conversely assume that this d is in domain. Conversely assume that d is in domain. So if d is in U, then there is nothing to prove. If d is in U, then there is nothing to prove. Now by previous theorem, d tensor 1 is equal to 1 tensor d, because d is in the domain. Now you apply the theorem. जहाँ पर हमने लिखा था a tensor b equal to b c tensor d, वहाँ पर वो set of equations आ गई थी ना, वो कौन सी theorem थी? That theorem was theorem number, I will mention that theorem number. So that's proposition 8.1.1. Now by proposition 8.1.8 we get the system of equations. हमें system equations मिल जाएगी of type 1. of the type 1 as required. So whenever we have D's in domain, then we have system of equations, and when we have system of equations, then D is in the domain. So note एक इसका, इस पर एक note एक लिखिए. The system of equations of the type 1 are called zigzag equations in S over U of length m, in S over U of length m, and the elements these elements used, they are called the spine elements. Okay, spine. The elements ui I equal to 0, 1 to 2m minus 1. The elements they are called a spine. Or called spine. तो इसका तो ये अभी zigzag theorem पर, this is the above theorem is called the above theorem. The above theorem is called the zigzag theorem. Zigzag theorem for monoids. तो नेक्स्ट लेक्चर में हम डिराइव करेंगे इसी zigzag theorem से, zigzag theorem for semigroups. This is called, so this is called zigzag theorem. In fact, it's called Isbell's zigzag theorem because it's actually given by Isbell. Proof ये Isbell's का नहीं है, it's not the Isbell's proof. तो ये मैंने बता दिया, ये proof है किसका, Stenstrom. Okay? This proof is not given by Isbell. तो कल के लेक्चर में हम zigzag theorem करेंगे सेमी ग्रुप्स के लिए, Isbell's zigzag theorem पर सेमी ग्रुप्स, और इसके लिए